Thanks for the invitation. So how much time do I have actually?
We stop at 3.
3. Okay.
So,
all right. Including questions
yeah.
and okay. Okay. So I'm going to give you a talk about fully dynamic case-center clustering. So this is part of our research, and it's about our effort for making our world dynamic. Okay. So it's a joint collaboration with the professor in Hong Kong and my student. So it's a part of my research where I focus on dynamic problems and I try to apply them in practice. So I try to bridge the gap between theory and practice. Sometimes I succeed, sometimes I don't. I hope this is perhaps a good example. So in case you're interested, I also have other research directions which are completely practical and just work well. The focus is to have something that works well in practice. All right, so what is the main focus of this talk is about fully dynamic clustering, all right? So the main issue is that we would like to deal with real-world data sets that are large, right, and that evolve over time. So, and nowadays there is plenty of examples, right? We have Twitter, we have the YouTube here, the brain, the human brain, right, the internet, right? So these are all very large data sets that evolve over time, right? So for example, in the case of Twitter, we have 6,000 tweets per second. Okay, so it's a huge amount of data that is generated over time. Facebook nowadays has 2 billion users. The human brain contains roughly 90 billion neurons. Of course, it depends on the person, right? But on average, this is what we observe. And then Google processes over 40,000 queries every second, right? So the bottom line is that we really need to have large-scale algorithms so as to make sense of this huge amount of data that is produced over time. All right, so what I'm going to present is one of my work, right? That was a collaboration with a student and another professor in Hong Kong University. And so these are a list of algorithms that can deal with dynamic environment, right? So feel free to, I don't know, contact me in case you find anything interesting or related to what you're working on. And so today we are going to focus on the fully dynamic case-center clustering, which received, was nominated actually for Best Paper Award last year at the World Web Conference. Okay, so the idea is that I'll try to give you a formal definition of the problem, okay, so what we would like to achieve in theory. And then I show you how these results, right, I mean, whether we have similar good results in practice as well, okay. So the idea is that we like to have something that is very interesting from a theoretical point of view and also appealing from a practical point of view, that in principle you would like to use this in a system, right, so as to make sense of a huge amount of data that is produced over time. So this part of this talk has also was given at Google New York last year, right? So they're interested in this kind of problems there as well. So to show that, you know, theory and practice sometimes can help, right, each other, right? So okay, so what is clustering, right? So I guess most of you, right, almost everybody here know more or less what is clustering. So this is one of the most widely used technique for exploratory data analysis. So for example, you can use clustering to find communities, right, in Twitter. So for example, these are all communities in San Francisco. You can see, right, so the geek community. There is also, of course, Twitter employees, right, music, hip-hop, foodies, right, and so on. Or you can also cluster the brain according to the functions of the brain, right? So similar functions will end up in the same cluster. And I guess here we can see in the picture 4 different clusters because there are 4 different areas of our brain. Well, at least depends, of course, on the granularity, right, of the clustering, but you could identify 4 different areas. All right, so in our case, we would like to deal, so clustering is already difficult per se, right? I mean, despite all the efforts that have been done in the last 50 years or something, we still don't know much about clustering, right? So there are still people that come up with new algorithms every day. So, I mean, this means that perhaps the problem is not fully understood yet, right? Here we would like to make it, even more, address maybe an even more difficult problem, which is to deal with dynamic clustering. We would like to maintain a good clustering at each point in time in an efficient way, okay? So for example, we would like to cluster YouTube videos as they are generated. We would like to cluster maybe like a geotagged tweets according to their geographic location where they are produced. Or we would like to cluster, in this case, we have car trajectories in Milan. Okay, so in this case, for example, these are all car trajectories, right? So we would like to put trajectories in the same cluster if their path is more or less the same, okay? So I guess, for example, you can say that maybe these are commuters from, the northwest part of the city and so on, okay? So this is a recent hot topic. Studying car trajectories, right, is very interesting topic. Okay, so so let's see, right, how to study the problem from a theoretical point of view, and whether we have good results in practice as well, right, at the end of the day. Okay, so first of all, let's consider a simple definition of clustering. There are many, right, and then I'll try to argue why this definition is also interesting, and then let's see, right, how to make an algorithm for this problem fully dynamic. Okay. All right. So in this case, right, we are given a set of points in the Euclidean space, and we would like to partition these points into k different clusters, so as to minimize the maximum radius of the clusters. Okay. So that is what we would like to do. It's a natural problem. Okay. So. It's one of the first things, right, you might want to do. All right, I said Euclidean distance, but we can use actually any distance, all right, any distance function that satisfies triangular inequality. Okay, so try to just give you an idea. So in case you miss maybe the technical details, don't worry, right? The main goal of this talk is not to, give a lot of technical details. It's mainly to show you that there is a simple technique that can deal with this simple problem, and I hope that maybe this will inspire also other, a solution for other problems you are working on, right? Okay, so let's see. For example, there is a very simple algorithm for this problem that can compute a two approximation guarantee. Okay, and it's very simple, and I'll try to give it to you again. If you don't miss it because you are not familiar with this kind of theory, don't worry. That is not the main goal of the talk. Okay. All right. So it works as follows. So we start with the whole data points, and at each point in time we pick one point arbitrarily. Right. This becomes a center, and then we create a cluster, including this point and all points. Yeah, okay, so in this case we build a cluster at the end, right? So we pick one point, and this becomes the center. And then the next point we're going to pick is the one that is further away, right, from the point we selected. Okay, so there are different variants of this algorithm, right? So let's focus on this one here. Okay, so we pick one point, we pick the one that is further away, right? Then we pick the third one, which is further away, and so on, until we selected exactly k clusters, k points, okay? And now we build a cluster by assigning each point to the closest center. So it's a very simple algorithm, okay? And it turns out that this actually gives us a two approximation guarantee for the problem. So this way we are going to build a cluster where the maximum radius of the cluster is at most a factor of 2 from an optimum solution. Okay, so which is quite surprising, right? It's a very simple algorithm. It can give you a two approximation guarantee for this problem. All right, so and for those of you who are familiar about NP hardness, right, you cannot do better than this unless P equal NP. Okay, so which is quite interesting, right? Very simple algorithm, and this is the best you can do, perhaps. So we are not sure about it, but there is some consensus that this is the best we can do.
Question.
Yeah, sure.
Why do you pick the cluster heads in the set of points?
Yeah, so in many algorithms in clustering, you would like somehow to choose a representative of the cluster, right? This allows you to deal with the clustering in a simpler way, right? As opposed to deal with all points in the cluster, you just elect a representative, right? And then you just deal with this guy. So in k-means, for example, this is the centroid. I don't know, yeah, if you're familiar with, yeah, most probably you are, right? In this case, is actually a so-called center, okay? So that is the main idea, more or less, why you just deal with the points initially, okay?
But if you take the version where the cluster head or centroid or whatever
yeah.
is the problem fundamentally different, or is not within the set of points? If you would take
yeah, sure. That's a very good point. Yeah, so there are some results that show that if you focus, for example, for k-means, you can show that if you focus on the set of points, as opposed to in the input points, as opposed to any point in the Euclidean space, you still you get an approximation, right? I now don't remember the approximation factor, but you know, a solution computed like this is not too far away from the solution computed where centers can be anything in the Euclidean space, right? So now for this, to be honest, I didn't check, but I would guess that the same thing holds, okay? However, I show you why this algorithm is interesting from a practical point of view. Okay, I will not argue about the two approximation guarantee, right? So for me, one of the interesting things about this algorithm is that it can compute so-called well-separated clusters, all right? So, and just to show you what is this, right? So these are clusters that look like this, and they are sufficiently spread apart. So, right, in particular, if you take the distance between 2 points in the same cluster and the distance between 2 points into different clusters, then this distance is smaller than the other one, okay? So in my opinion, this is the easiest clustering problem you can deal with, right? So it's pretty natural, right? So to make it even more apparent, right, you can think that these guys are spread up more apart, okay? And this should make the algorithm, the problem, even easier, okay? All right, and the algorithm I told you before can actually find, so if there are k well-separated clusters, the algorithm I told you before can actually find them, okay? And this is not the case for k-means, for example. K-means might not be able to find this. Even if you iterate k-means for an exponential number of times, it might still be the case that you don't find the well-separated clusters, okay? So that is an interesting property of this algorithm versus other widely used algorithms such as k-means, okay?
Well, I guess it depends on the initialization step of k-means. If you take the same initialization step as
k-means plus plus, right?
Yeah.
So in
just k-means, just your initialization is not random except for the first one.
It's completely arbitrary in this case. So any point is fine, right? In k-means, you take point randomly, right? So in that case, you can show that the probability that you select at exactly 1 point per cluster is very small. It's 1 divided an exponential function of the input of the set of points. So in order for this property to be satisfied, you need to iterate the algorithm an exponential number of iterations and then pick the best among all iterations so as to make sure that this property is satisfied, right? So this is, I mean, I'm not saying that this is better than k-means, right? I'm just saying that this simple algorithm exhibits an interesting property, which is pretty natural in my opinion, that is not captured by k-means, okay? Okay, all right, so I hope I convinced you at least that the problem is interesting, right? Now, if you know that, your clusters are not exactly well separated, but more or less well separated, you can use this algorithm, and then, maybe you can already find a good solution with this very simple algorithm that can be implemented efficiently. All right, so now, in the rest of the talk, we try to make this algorithm completely dynamic. So we would like to show that if we insert points or remove points, we can recompute a solution efficiently without recomputing everything from scratch, right? Okay, so in particular, I would like to show you, at least sketch an algorithm that can do that while using only a logarithmic number of operations per update on average, okay? Where the logarithmic in the size of the input. Sure.
So, what about this algorithm if I give you k is equal to 3?
So this is still a static algorithm, right?
Yeah.
Yeah, all right. So the problem is if there are k well-separated clusters,
It finds them,
right?
But
you don't know k. But then you can try different values of k, for example, right? So if you don't know k, you can run this algorithm for different values of k, right? And then, yeah, sure. Okay. Yeah, so as I said, for example, k-means cannot solve this problem. K-means plus plus is a bit better, but you can still show that there is some high probability, some probability that you don't find them. Okay, so this find the well-separated cluster with probability 1. Okay, so I think it's really a nice property. This is not only, of course, this is not the only one. This is not the only algorithm that satisfies this property. For example, you have a single linkage, and there are others, right? So again, I'm not saying this is the best algorithm. I'm just saying this has an interesting property, and since we can make it fully dynamic, that is very interesting because there are just another algorithm that is fully dynamic, right? So that is very appealing in my opinion. Okay, so all right, so also to show you that this is interesting from a practical point of view, as I said, I gave this talk at Google, and at Google there are many people there. So for example, I could find this for papers working on some variants of this clustering problem, okay? So, and they also have efficient implementation of this at Google. Just to show you again, right? Sometimes, you know, you assume that what is good in theory is not good in practice, right? And vice versa. And, you know, part of the talk is to try to show you that we can do, you know, we can achieve the best of two worlds, right? In some cases, okay? Okay, there are other approaches, of course, for the same problem in where the data is not fully dynamic. So, for example, there is this work from Vincent Cohen-Haddad, who gave a talk here. I think there was a workshop on graphs, right? And he gave a talk, again on clustering, but I don't think he gave a talk on this. But in this case, right, he was able to deal only with some specific settings, right? So he was able to deal with the case where the points are deleted and inserted in some given order. So in some cases, this might be interesting in practice, but there are many cases where you might actually want to deal with arbitrary deletions, okay? So for example, you know, nowadays, right, we are very concerned about privacy, and we should be. So you might think that you might want to delete a point, and this could be, you know, YouTube videos or something, because of privacy concerns or because it is inappropriate or something, right? And then, you know, you cannot make any assumption on how these points are removed. Also, there is also the right to be forgotten principle, right? If you want to delete your account in Facebook, you should be able to do that, right? And again, you cannot make any assumption on how these accounts are deleted or created, right? And also the very same problem I mentioned before, like the problem of clustering trajectories. Again, in that case, you would like to deal with the arbitrary insertions and deletions, okay? All right, so I hope I convinced you that there is really a strong need for dealing with fully dynamic algorithms where we don't make almost any assumption on how points are deleted or inserted, okay? All right, so let's see, right? Okay, so I'll try to, depending on the interest, I will focus more on the theoretical part or practical part, so feel free to, you know, ask questions so I will figure out what is the most interesting part in your opinion, right? All right, so first of all, let's see what do I mean by fully dynamic model, okay? So we are assuming that there is a little cute devil here that will decide in advance which points must be added and must be removed. Right, so he said, okay, he or she, sometimes the devil is a woman, right? So he or she said, okay, I would like to add P1, P2, remove P1, then I would like to add P3, and so on, okay? So he or she decides, right, the set of points that have to be deleted or removed up front, okay? So our algorithm does not know what he or she decided, okay? So we don't make this assumption. We only assume, and maybe there is a tiny assumption if you want, that this algorithm cannot predict our random choices. So in practice, if you want, this is equivalent to have a very good pseudo-random number generator, okay? So if the pseudo-random number generator is good enough, then you cannot predict, right, the sequence of integers that are generated by the generator, all right? So if it's good enough, then our algorithm can deal with any arbitrary deletion, okay? Okay, all right, so of course, right? So the problem is this then. We would like to maintain a good clustering, okay, at any point in time. And we would like to maintain a clustering with a small maximum radius, okay? So one solution, the simplest you can think of, would be to recompute everything from scratch. So whenever you add a point or you remove a point, you run the algorithm I showed you before, right, from scratch completely, okay? And then, of course, right, this guarantees the property that, you know, we have at each point in time, after every insertions, after every deletions, an algorithm with a small maximum radius, okay? All right, of course, that is not ideal. So if you count the number of operations you perform in this case, you have a large number of operations, right? So in particular, every time you remove a point, you need to process all other points that have been inserted up to now, and then the number of operations is large. So if you want to deal with 6,000 tweets per second, you cannot recluster all the tweets every time you have a new tweet, right? I think everybody agrees on that, okay? Okay, so maybe I will just give you very quickly the idea. So let's see, right? Let's see if I will be able to give you the main message here. So let's assume we know the value of the optimum solution. This could look like a strong assumption in the beginning, right? But then it turns out we can easily alleviate this assumption. But let's suppose we know the optimum radius R of an optimum solution. All right, so let's consider this variant of the algorithm. So we do the following. At each step, we pick one point arbitrarily, okay? And now we build a clusters. So this becomes a center. And now we build a cluster containing all points that are within distance 2 times r from this point, okay? All right, so we remove these points, and we iterate until we have exactly k clusters. R is the optimum solution. We are assuming now that we know the optimum solution, the maximum radius of an optimum solution. Okay? Okay, so we iterate. And then we can show, and it's very easy to show, that if we are able to cluster all points, then we have a clustering, right, with maximum radius 2 times r, right? I think everybody can see that, right? At each step, I take a point. I put all points within 2r from that point, right? If I'm able to cluster all points, then the maximum radius of the cluster is 2 times r, right? In case I'm not able to cluster all points, okay, then I can tell you that, you know, this cannot be the optimum, okay? Because in that case, I can find k plus 1 points that are at distance larger than 2 times r. So since I have to cluster k plus 1 points that are at pairwise distance larger than 2 times r, then at least 2 of these points must end up in the same cluster, right? And then the radius of the maximum cluster is strictly larger than r. And then r cannot be our optimal solution. Okay? So that's a very simple lemma. Okay. So, all right, so let's see how to deal with random deletions. Okay, then I'll try to give you an idea on fully dynamic deletions, and then we move on to the experiments. Okay, that is the roadmap. All right, so the insertions do not change. Okay, again, if r is the value of an optimal solution, we can cluster all points. If we didn't guess R correctly, okay, so we can show that R cannot be an optimum solution, okay? And we can maintain this for any value of R, all right? So you can think that we execute this algorithm for any R if you want. And then if you want to know how to deal with the practical case, I can give you a hint, right? For now, for simplicity, we can assume that we do this for every possible value of R. So what we do if we have random deletions? So we still want to maintain the same property, right? We still want to be able to cluster all points in case something, in case we add or remove points, all right? So we do the following. So if x is not a center, we can delete it. No problem, right? I hope everybody agree with me that the maximum radius is still 2 times r. We just remove a point that is not a center, no problem. If x is a center, then we are into trouble, right? Because these leaders, representative of the cluster, play an important role. If you remove the leader, right, then it's going to be a mess, right? So in that case, we recluster everything, okay? All right, so this might seem to be bad, right? But it's not that bad. Because at the end, right, you have only k centers and cardinality of x points. So the probability that you delete one of these centers is k divided by cardinality of x, which is very small. And the cost for reclustering everything is k times cardinality of x. Okay? So if you do it on average, then we have k squared per update operation, which is not bad at all, right? Okay? So this is more or less, right? Simple math, compute the expectation. Okay? All right, but these are random deletions, right? This is not what I promised in the beginning. Okay? So I'll try to argue, right, why this is bad in practice and in theory. So suppose that our deletions are actually not random. Remember, we have still this little devil that is making our life really difficult. Okay? So then the devil could say, all right, I don't know which center is here, for example, but I know that there should be a center here. Okay? So then I can add and remove these points. So I first remove all of them, then I add them back. I remove all of them, and then I add them back. This way I'm sure that every 4 points removed, I will remove at least one center. So with only 4 operations, I will have to recluster everything. So in this case, our adversary will really make our life difficult. All right? Okay? So this is why we cannot assume that we have random deletions. All right, so I'll try to give you an idea in this short time to deal with the fully dynamic case. And of course, if you want to know the details, either write to me or check the paper. All right, so the key point is the following. Maybe I'll show you this with a picture, right? All right, so we have this cluster so far, all right? And suppose that these are the centers. Okay, so let's consider an arbitrary ordering of the centers from C1 to C5. Okay, all right, so now suppose we delete this guy over here. Okay, so now the simple algorithm would recluster everything. All right, so the smarter algorithm would do the following. It would recluster only C3 and all the clusters that come after C3 in the ordering. So only these points will be reclustered, as opposed to everything. I mean, these points are still good, right? So why we need to bother, okay? All right, so now these are the points that we're going to recluster. How do we recluster them? We do the following. So at each step, we pick one point, uniformly at random among all these points, and we say this is the center. We build a cluster again containing all the points within distance 2 times r from the center, okay? And we iterate. So, but now observe one thing, right? The probability that we select this guy as the center is very small, right? Is 1 divided by 15, where 15 are the points that we are reclustering, okay? So now we iterate. We pick one point among the yellow points uniformly at random, right? So for example, this guy, right? This becomes a center. And now observe that the probability that we select exactly this guy is 1 divided by 11th, okay? And we iterate until we recluster everything, okay? So now why I told you about these probabilities. So the idea is the following. if the adversary decided to delete, for example, this guy, okay, this guy becomes a center with probability 1 divided by 15. Okay? And in that case, the number of operations I have to do to recluster everything is 15 times k, right? So with probability 1 divided by 15, I have to recluster a lot of points, and the number of operations required is 15 times k. So on average, the number of operations are k, right? That is the idea. So it's a very simple idea, but it's powerful, right? Because now we can guarantee that somehow the probability that one guy is the center and the amount of work I need to do to handle these deletions cancel out. Okay? Yeah?
In real application, if you're so unlucky that you hit this thing, practically the algorithm doesn't work anymore. I mean, if Google is running something like that,
yeah,
it can work. When some very bad deletion like the one you described happens, then maybe the algorithm doesn't work anymore because key is very large. Right? In probability, it's a very unlikely event.
Oh, all right, okay.
Nothing.
That's a very good point. So you're saying that...
Cancel out is a bit optimistic, right?
Oh, well, no, it's not optimistic, right? So math is not optimistic.
Yeah, right.
But here it's math. It's 1 divided by 15 times 15 times k, and this is k, right? This is math, okay? But now I think you see what is your real point. You're saying that on average, right, we have a small number of operations. But is that true for every single execution of the algorithm, right? If this is true on average, it might not be true for every single execution of the algorithm. So we can show that this also holds with high probability, okay? So that there is a very small fraction of cases that can go wrong, okay? And I'll show you some experiments to double check this as well. That's a good point, okay? Okay, okay, so I hope you got more or less the main idea. And then, right, so, okay, I will not show you the analysis, right, of course. Let me just summarize the results. So we can say that we always maintain a 2 plus epsilon approximation as opposed to a 2 approximation guarantee, okay? So our approximation guarantee is slightly worse than what we showed before, all right? And moreover, perhaps this is one of the most interesting things, is that the expected running time is logarithmic, right, in delta, where delta is the maximum distance between, so it's the ratio between the maximum distance between 2 points and the minimum distance between 2 points. Okay, it's a bit technical, but just think that if delta is polynomial, then this quantity is logarithmic, right? So the amount of work is logarithmic in the size of the input. And it works in the fully dynamic model, where the fully dynamic model is what I showed you before, where the adversary chose all the operations in advance, right? Which is very good, right? I mean, whatever the adversary does, this is true, okay? That's very nice, in my opinion.
Why is didnt positive? You may have 2 points in the same place. Why does didnt matter?
Because, all right, so because I told you that, all right, so here we are assuming that we don't have 2 points in the same place, but it's not a problem, right? So this holds, of course, if in the case you don't have 2 points in the same place, but then you can easily deal with that case, all right? So this is just for illustrative purposes. Don't think that this can deal any problem. So now why this is important? Because I told you we're actually assuming that we know the optimal solution, right? In practice, of course, this is not true, okay? So what we do then, we guess the optimal solution. So in particular, we try different possible values of the optimal solution, and these are all the values that are between the mean and the max in the worst case, right? We are smarter, of course, than that. And rather than trying all possible values between the mean and the max, we actually bucketize the interval the mean and the max, and we try only the integral power. So this is specified here, right? These are the technical details. I said, okay, maybe I'll not tell you unless you complain. All right, so that is the idea, right? So we basically consider only the values that are in this range between the mean and the max, but only the integral power. All right, so we consider the mean 1 plus epsilon, the mean 1 plus epsilon square until we get to the max, right? Okay?
So the mean matters. Yeah.
So the mean matters, but you agree with me that this is true, right? That then the cardinality of gamma, so the set of values you try, is this quantity, right? So now the ratio between the max and the mean is, for example, n, right? This is log n, right? Which is very good, okay? All right, so in this case, the mean do matters, of course. But then in the case, but here we're assuming that there are not 2 points in the same spot, okay? If this is true, we can deal with that case, no problem, right? I mean, it's just, rather than having 1 point, multiple points on the same location, you just have to remember that you have n points on the same location, right? And you consider this as 1 point. So that doesn't cause any problem, okay? That's a very good point, right? You said, okay, what if the mean is equal to 0, right? But I mean, but that doesn't cause any problem.
Yeah, you mean in the algorithm itself, I agree, but for the choice of R of the radius?
No. So the idea is this, right? If you have a situation where you have that 2 points are in the same location, you can transform this in a situation where all these points are merged together, and you just remember that you have n points at that location, okay? And then everything else applies, okay? Yeah, sure, that was a fair point. Okay, so I will not bother you furthermore with theory. I hope you got the main idea. I think it's very simple yet very powerful, right? Again, there are only 2 algorithms that are fully dynamic, and this is one of the 2, right? So I think somehow it's very exciting that with a very simple algorithm we can deal with this complicated problem. So let's see now in practice, right? Some of you raised some concerns about practice. Well, let's see what we can have in practice, right? Okay, so my student, run all the experiments, right? So these are the settings. All the code is publicly available. It has been written in C++, right? So it's or C now. I don't remember exactly. It's very efficient, all right? Anyway, I'll show you some results now. So we consider 3 different data sets. Twitter, so 20 million of tweets with GPS and timestamps, okay? Flickr, 47 million pictures with GPS and timestamps from the Yahoo Flickr Creative Commons. And for some reasons, we have 83 million trajectories from 500 taxis in the city of Portugal, right? For some reason, this data is available, okay? And for us, this is very good because this is an interesting data set. So trajectories are updated every 15 seconds. Okay? So a naive algorithm would have to recompute everything from scratch every 15 seconds, which is not ideal. Okay? All right, so now we have trajectories, and we have these GPS coordinates. What is the distance? All right, so in the case of GPS, we have the gray circle distance. Okay, this is a metric, and it's still fine for our algorithm. In the case of trajectories, we compute the distance with the Hausdorff distance, right, which is defined as follows. And this is a metric, and we are still fine. So we can deal with all these cases, all right? The interesting thing is that in the case of trajectories, all right, we cannot make any assumption on how these trajectories are updated. So for example, the framework I showed you in the beginning, one of the related work that made some assumptions on how the input points are deleted or removed cannot be applied in this case. So it is in this case that our algorithm gets, gets the possibility of showing all its potential, right? Because in this case, we cannot make any assumption on how trajectories are updated, deleted, or removed. You have a question? I can tell.
No, just the algorithm works because initially you said in the Euclidean space. So in any metric space, you have the...
Initially I said that, but then maybe, yeah, so it was written, so in any metric space, that's true. I said that in any metric space, but anyway, yeah. So it's any metric space, yes. As long as we have triangular inequality and everything is fine. Okay. All right. So let's see. Right. Okay. So now, right, usually when you run perform two algorithms, right, you have, it's very simple to show the approximation ratio, right? You adjust two data points, right? On one hand, you have the quality of the solution of one algorithm. On the other hand, you have the quality solution of the other. You just need to compare them, right? But here we have a lot of updates. So we would like to show that consistently, in all updates we perform, we are good, right? So and one way to show this, right, is to show the median, the first and the third quartile, the maximum and minimum approximation ratios. So this way we have a full picture of what is going on, right? So for example, one way to read this plot is that for k equal 10, right, the approximation ratio of our algorithm, which is the blue curve, is always between 2.2 and can be even better than 2, okay? And for example, for the other one, which is the red curve, right, is within this range, right? And the median is this, okay? So this way you can really get, you know, a summary of what is going on the whole data set, not only one point.
You compute approximation ratio against the naive solution, right?
Okay, that's a very good point, right? So approximation ratio, you need to compute an optimum, right? But of course, this is an NPR. It is NP-hard to compute an optimum solution. But we can compute a lower bound on the optimum solution, and so we compute against this lower bound. So in particular, the fact that we are here, it doesn't mean that we are away a factor of 2 from the optimum. We can be even better because we don't know the optimum, right? But for sure, it cannot be worse than that. Okay. All right, so this is approximation, and we can see an interesting thing also here is that we are actually better than the worst case analysis suggests, right? So the worst case analysis says, okay, it's a 2 approximation. In some cases, we can be better than 2, okay? So sometimes, you know, practice is better than theory, right? Okay, here we change epsilon, maybe not so interesting. Here we compare the running time, okay, which is also one of the things I'm proud of. So our algorithm is the blue curve, the other one is the red curve. So it's true here we are slower, but we are still talking about half millisecond per update, okay? So whenever you remove a point, on average, it takes less than half millisecond to update your clustering, right? So we almost can deal with 6,000 tweets per second, right? So I mean, which is pretty good, right? So it's pretty good results. So we are a bit slower than the other, but we are much better in terms of approximation guarantee. So in particular, we can find well-separated clusters if they exist. The other cannot, right? So that is a very good point. Okay, and now just to write, so one of the criticism was really a fair criticism, right? So it says, if I understood well, right? It says, okay, on average we are good, but what on a single run, right? What happens, right? And this is what we show, right? We have this theorem that tells us with high probability we are also good, right? But is this true in practice as well? Here we show that, so here we plot the frequency, right? So this means, for example, that we run our algorithm and 50 or even more, like 60 rounds out of 100, the average running time was 0.6 right, milliseconds, I think so. How do you say that? Well, 1/10 of a millisecond, right? Yes. Right. So we deviate from, you know, the average only in a very few cases, and we didn't deviate much. You know, in the worst case, it was twice as much. Okay. So very good on average, but very good also for a single run of the algorithm.
This is with a sample of how many points?
So these are 100 rounds of the algorithm.
How many data points?
So this is for, I didn't specify here. So it's one of these 3 data sets. Now I don't remember, right? So between 20 million and 80 millions. Okay. All right, and we have similar results for trajectories, right? And this is the interesting case, right? Because this cannot be dealt with by an algorithm that makes some assumption on how the points are inserted and deleted. Okay. All right. So just to summarize things, and then let me know if you have questions. So I think this algorithm is interesting from a theoretical point of view. Remember, right, that we cannot do better than 2 unless p equal np, and we have a 2 plus epsilon approximation guarantee. All right. Also, some people can object that we use a lot of memory, but it can be shown that if you want a 4 approx, and we have a 2 approx, then you need a lot of memory. Okay, so this is something that you cannot escape from. And then experimental evaluation is very good, right? We have good results not only in theory. In practice, this is what happens, right? We require less than half millisecond per update on average. In practice, also the approximation ratio is very good, all right? And then it performs the state of the art, right? Smaller radius, it is fully dynamic. We can deal any arbitrary deletions and insertions. And is also slightly, but it is slightly less efficient. Perhaps that is the minor drawback. Okay, so I think maybe just to give you an idea of what we are working on, right? So before I mentioned these well-separated clusters, right? We want to see whether we can deal with clusters with weaker property, right? So for example, we would like to see whether we can deal with weakly separated clusters. So these are clusters, right, that have basically, well, maybe again, the picture is self-explanatory, all right? So in this case, we would like that I consider one point. We would like the cluster to have this property, right? If I consider one point, and then I take another point in the cluster, I would like that this distance is smaller than distance between this point and the point in another cluster, okay? So this is a weaker variant than what I showed you before. All right, so which algorithms can deal with this, okay? So there are some variants of some algorithms that can find weakly well-separated clusters, but cannot deal with outliers and cannot deal with a fully dynamic environment, okay? And this also opens up like an interesting direction, right? As I said in the beginning, we still don't know much about clustering, which is surprising because this is one of the most natural problems, right? That we have been working on many, many years. But still, you know, the widely used algorithm cannot find well-separated clusters, for example, which is somehow disappointing, okay? So can we devise like an axiomatic approach to clustering? Can we say, okay, these are the properties we would like from our clustering algorithms, and can we devise an algorithm satisfying these properties, okay? And can we make everything dynamic? So I think this will keep us busy for a few years in the future, right? Okay, thanks a lot for your attention, and I'm looking forward for your questions. Yeah.
How did you consider deletions in the data sets? Because I see how naturally you consider additions, but...
Very good point, yeah. All right, so yeah, so this is what we did, right? So in the case of Twitter Fligger, we maintain a sliding window. So we wanted to cluster only the, all the points that have been posted, for example, in the last 1 hour. All right, so this is a sliding window. At every second, you have a new point that is added and the oldest one that is deleted, right? And the other approach can deal with this setting. So a sliding window model can also be dealt with the other approach. For taxi trajectories, things are different, right? In that case, right, we know exactly. So you have just trajectories that are built over time, right? You have a taxi that so far did this, and now did this, and so on, right? So it's pretty natural what we did, right? At every point in time, we had a point to a new trajectory, okay? But notice that this is more general than this, right? Because you cannot assume, so the trajectory that is updated is not necessarily the oldest or the most recent one, right? So in that case, anything can happen. And so this framework does not fit in this framework. So in order to deal with this, you need a fully dynamic algorithm.
And still for this, you remove the
No, in this case, you don't. You don't remove the trajectory. Because, I mean, the problem is basically, right, so this is what I showed you in the beginning, right? So you want to cluster trajectories in Milan, right? So for example, you know that all these trajectories are very similar, okay? So as you build the trajectory, you would like to get a better cluster, right? So maybe there is one guy, for example, look at this, right? So up to now, up to here, you would put all these trajectories in the same cluster. But now, after this guy deviates on this, then you will get a new trajectory. You know that this trajectory here is different than this trajectory here, right? So you just have a more refined trajectory if you want. You don't update, you don't remove the oldest one, okay?
Okay, and last question. When you use the time sliding window, what percentage of the data set remain?
Well, this depends on the setting, right? So if it was 1 hour, let me see if this is somewhere, otherwise I need to check the paper. Well, I think it really depends on the setting. I think in our case, we consider 1 hour of tweets, all right? And in that case, it's a relatively small portions, right? But imagine you consider all, last month of tweet, or all tweets that have been posted so far, depending on this, right? So if you want, right, in the case of Twitter, if you want to have like short events, I don't know, like an exhibition in Paris that doesn't last too much, then it will be, you will set the sliding window to a couple of hours, for example, right? But if you want to have, I don't know, like a festival, like, I don't know, the theater festival in, where is this, in this city, Avignon, right? This lasts maybe 1 week, and then maybe the sliding window will be larger, all right? So it really depends on the setting. But you're right, in some sense, that the amount of data in this sliding window is relatively small to the compared to the whole data set, right?
How did you choose the radius in this experiment?
So the radius, again, right, we tried all possible radius.
Okay, so you choose a...
I mean, this gives you a 2 approximation guarantee. So one of these radius is guaranteed to be, right, at most a factor of 2 from the optimal solution.
But you don't know which...
We don't know, no, but then you can choose the one, so you try all possible ones. The first that is able to cluster all points is guaranteed to have a 2 approximation. Okay? So, and you know for sure that this is a 2 approx.
For one separated cluster?
No. All right. So, well separated cluster is a particular case. So there is a more general problem of minimizing the maximum radius. Okay? And this still gives you a 2 approx for this more general problem. Okay? Yeah?
So thinking of the problem differently, if you have your set, it could be dynamic, but you could pick, say, k points at random,
Yeah.
perhaps with some repulsion of some, and look at the Voronoi cell of those.
And look at the
Voronoi.
Oh, okay.
Because you're on the metric space.
Okay.
So you would have something completely dynamic as well, right? Because if you delete or add points with respect to the, which are not the points that you have selected for the point process,
Okay.
you would just add things or delete them from the Voronoi cells, and you would resample.
But then, yeah, okay, that's an interesting idea. But how much operations you will need to update this? You know, the interesting thing here is that we are able somehow to balance the number of operations we perform with the probability that, this expensive operation happens, right? And then these two things cancel out. I'm not sure that in this setting you can do the same. Perhaps you can, right? But we have to check the details, right?
Well, if you don't delete the points that you have selected for the cluster heads of the point of the Voronoi cells, then
okay. In that case, you're fine.
Then you're fine.
Yeah, sure. But what if you remove the centers?
Then you have to resample to add 1 point and at random, and so
you have to resample.
It will be completely local.
Right. Okay. We have to check the details. I see. The important thing is to guarantee that the amount of operations you perform, somehow is not too large, and this happens with low probability, right? So if you are able to guarantee this, then you're fine. And now I don't see, but yeah, we can discuss, or I can also think whether this idea is interesting. Sure. That's a good point. Mm-hmm.
Okay. Thank you.
Thanks a lot.